Well, it's a great honor to be here and see Libby and Alejandra again. And we had a fantastic symposium in Puerto Rico in his honor, and Randy was there and others were there to raise money for the scholarship that Ramon has supported for so many years. And I guess you can't start a talk with Ramon without a joke, so I'm happy to be here from potentially the 11th province of Canada. But, you know, it's really been an honor. You know, Randy worked with Ramon when he first got out of Cornell and came to UT with Breen, and by the time I came there, I had Jan Olick, who's here, and Luis Archuleta, in which I sat there and just shoveled aggregate for them for basically a year to learn everything. And then after that, spent the next time of my life with Ramon. And so he became a fantastic mentor to me, but also a colleague and a friend of almost 40 years. And it was really sad to see him go. But when we look at this kind of impact that he had on so many of us, it was that he understood, and throughout my talk I'll talk a little bit more about some of that impact. But he was a person, one of the things you have to understand, when he came to Penn State, or to Texas, he didn't know much about fly ash. Texas, I mean, he came from New York and Cornell. They didn't use fly ash. It was not permitted to be used in New York, Pennsylvania, any place in the Northeast. So it was not a thing. But he knew opportunities. And you see that in his consulting, you see this in his education. He learned throughout his lifetime. And that's a great lesson for all of us. He learned about fly ash when he came to Texas because of the Resource and Recovery Act. In 1976, the Congress passed this thing. And it sat around for 10 years. It didn't do anything. People didn't. Finally, in 1984, it realized, well, it's got to be fully enacted by 86, within 10 years of the enactment of the original law. And nobody had done anything about it, and the EPA decided in 1984, in 83 and 84, that fly ash would be the first product, the first giant-sized material that must be recycled by mandate. And of course, no one was ready for this. The Army Corps and the Bureau of Reclamation had used fly ash in dams and things like this, but nobody was going to put it in a bridge. What's the matter with you people? You know? And so he had this foresight to say, let me convince TxDOT that we need to be in the front of this. And not on the theoretical side. We can study that, but also how do we practically use it? And so as we went through this thing, we were using the nation was using about 2 to 3 million tons of fly ash, mostly in foundation work and low hydration work. But he saw this and convinced them, and in the next few years, in the next 5 to 10 years, he went through a whole raft of graduate students and about $1 million in funding from TxDOT to change the way we see fly ash, that it's not a waste material, that it is a technical addition to concrete that makes it better in almost every way. And so he spent this time to do this. Before this, the EPA just had anecdotal information. They had no technical data, but they made a mandate, and it said any state that doesn't allow it will not be granted funds from the federal government after January 28th, 1986. And so everyone adopted the federal standard, which was based on nothing other than a bunch of old studies and an NCHRP report which brought all this stuff together and said, well, 25%. Everyone has to use 25%. And nobody knew what to do with that exactly. And Texas actually lost its funding for about 3 weeks because they were going to allow 35% in certain circumstances, and it wasn't exactly the same as the federal standard. So FHWA had to evaluate the Texas spec to see if it should be used. But when we look at this kind of stuff, we see that there was this money. Everything was driven by money. And it turned out to be a fight between the EPA and the Federal Highway Administration. And the EPA won. The Federal Highway Administrator at the time fought this. He said, nobody's ready for it, nobody's going to do this, nobody should do this, it's not good for highways, and said, put it in pavements and leave it alone. And he ended up having to go to a federal court to impose the EPA mandate. And the FHWA lost against the two government agencies fighting each other. But Ramon, through these two projects, 364 and 481, he trained a whole group of people, okay? I mentioned Jan and Louis already, but Joseph Fabias, Larby Sr., Scott Anderson, who will be the future president of ACI, Bill Eckert, Rich Barrow, Cesar Constantino, which many of you know, okay? Jim Aronson, Hope Villanueva, Kareem Hitachi, Reed Freeman, John Myers, and myself, and many others. I maybe don't all know them all. But these were to create guidelines to which create great opportunities and to show that it is technically smart to use it. When I came to Texas in 1984, they were getting paid $40 a ton to take fly ash away from the utilities. Okay, the utility had to bury it, and it cost $40 a ton. So if you were willing to take it, they'd give you the $40 and say, take it. And now, now it costs more than the cost of cement. But when we look at this, we see that these results led to greater investments. And it wasn't just at UT. We saw this investment. We saw people at Purdue. Okay, we saw people at University of Wisconsin at Milwaukee. We had people in North Dakota. We had people across the country, universities, looking at different aspects and providing some collaboration so that the fly ash industry and the admixture industry, all of them had to come together, eventually the cement industry coming on board and saying, this is the new reality. And I think you see the parallel today when people are trying to make green cements. This same kind of reality now exists in a new paradigm. But Ramon was ahead of the game here, and he wasn't afraid to learn something new, which again is one of the big lessons here. And I think the thing we found out was that chemistry was important. It wasn't just, well, let's just try it and see how it works out. No, we analyzed every bit of fly ash. We studied the glass particles. We studied every plant. I mean, there were 37 plants in my research. Every one of them was studied with SEM, with X-ray diffraction, with everything before we went and used it. And I had more than 10,000 samples going at any one time, and we were monitoring them for 3 years, every sample for 3 years. It was exhausting. But we found what worked and what didn't work, and we could connect it to the chemistry. And then other people could look at that chemistry and say, can we alter the chemistry? Can we collect ash differently? Can we classify it differently? How do we get it so we get a better product? So when we look at these kinds of things, we looked at these changes, and then the growth of the specifications. ACI recognized this. Back in those days, we had ACI 226. It covered everything, right? It covered fly ash, it covered slag, it covered silica fume, it covered natural pozzolans, everything. And then it splits because this has become a giant industry. And it had a lot more technical data available. So it splits into, three different committees. It's actually 232, 233, and 234. So 234 was silica fume, 33 was slags. And then later on, it's even become now, in the new paradigm, now 232 is split into 232 and 240, where 240 is natural pozzolans and processed pozzolans. And so you see, hardly anybody wanted to even be on 226 back in the day. Nick probably remembers. I mean, it was a small committee. It was chaired by Bud here. And so, I don't know, I was 31 years old and I was already the chair. Bud didn't want to do the chair anymore, and neither did anybody else. Who cares about fly ash? So it made me the chair of an ACI committee, and I was 31 years old or something. But it grew, and the specs grew, and people became more understanding of it, and now people wanted it. States start putting it into their specifications and say, you must use it, because it's the thing that reduces permeability, and conductivity. It creates an environment by which salt and chlorides won't enter as quickly. It helps you with the diffusion problem of salts. And so as we look at some of these kinds of things, we start to look at this created the environment for which we can talk about more resilient infrastructure. So this has been the key to expending much of the life of our infrastructure. Later in my career, I ended up doing the 100-year highway in Pennsylvania. It's I-99. But 25 bridges were built for the same cost as they would have done otherwise, but paying attention to quality control, slags, fly ash, silica fume, the amount of this collaboration that Carlos talked about. When the designer and the contractor and the ready-mix producer and project management and the owner talk about what are we going to make the bridges out of on a weekly basis until they actually get built. And everybody was on board, and they found out it ended up costing less. So they allowed them to spend more money on quality control, which even made them better. And those things now, it's 30 years later, they're basically, no maintenance has been required since they've been built. And so I think we will see them. I won't get to see them, but someday they'll get to 100 years. We look at this not just we looked at sulfate resistance, salt resistance, ASR, impermeability. All of these things, each one required a different type of design. You're not going to get low heat and all of these at the same time. So you had to learn how to optimize which ones. And Ramon taught us those things. He said, don't try to be all things to everything. It doesn't have to make a super cement. Figure out what conditions these people have and design it for that. You don't have to design a thin structure for heat problems. It's not going to have heat problems. So look at what you can do. And, reducing the amount of total cementitious material reduced cracking. So every highway department that said, oh, let's put 7 sacks of cement in a bridge deck, and if that doesn't work, put 8 sacks in. Well, you just get more cracking. The answer was 5.5 sacks. Going to go less. And you got a much better deck, and it didn't crack, and it was impermeable. So this leads you to this idea that, we shouldn't confuse. And the complexities of what could be versus what is durable and long-lasting, and all of these kinds of things, they don't have to be expensive. That well-trained crews and quality control matter, and Ramon understood that. When he was involved in a job, he was up to his boots in it too sometimes. As Randy showed I can't even show you my gear from the Ferguson laboratory because it was a set of overalls that stood by themselves after 4 years. I didn't even have to put them in a locker. And so they were so full of cement paste that it eventually had hardened. They were just kind of an armored suit. And I don't even know what happened to those anymore. But when we built these things, we ended up with these extraordinary possibilities. And this is one of those bridges in the 100-year highway. I mean, these are giant bridges we built. These aren't small overpasses on an interstate. These are long bridges, 25 of them, and every one of them was designed with a different concept to make them last 100 years. And they're all doing great. They didn't want us to build any control bridges that would fall apart. You can understand that. I think they have a whole state of those. So, but today we look at, 12 to 13 million tons of fly ash goes directly into the concrete industry, into the reinforced concrete industry. It could be even higher, but we see the reduction in coal production now for greenhouse gas emissions and so forth. This is going to be harder and harder to do. You're going to have to find a new way to do it. And it's one thing, we put ourselves out of business. But the fact is now we're mining fly ash that we didn't use before 1986. We're digging it up and processing it and trying to use it again, because all of that stuff was there for 40 years before then. And so I don't know how we'll do with that, but we'll see. It's happening already, and it's productive. When we look at the amount of CO2, which we didn't think back in those days was even important. Nobody cared about how much CO2 cement made, how much it took to produce or whatever. But if you just look back at the amount of fly ash that has been put in concrete in Texas, and TexasDOT gave me these numbers a few years ago, that research, that $1 million of research they invested, has saved more than 1 billion tons of CO2 just in the state of Texas. 1 billion tons of CO2. And you look at, that wasn't its intent. But the reality was finding a great use for it turned out to be a solution to helping with the climate issues. So we look at also, that we got to the 100-year highway. When you consider that the highway now lasts longer, it's no longer going to be rehabilitated at 25 years and completely replaced at 40 years. Now you talk about 67% savings in CO2 for every bridge you build, because they last so much longer. And you don't have to rebuild them and reuse new cement. People often forget, let's see if there's a little, is there, oh yeah, here we go. If you look up here, concrete is one of the least embodied energy materials compared to aluminum or copper or steel or glass. We use more of it per ton, but it's actually a very environmentally friendly material because most of it is sand and gravel, right? And these are not high-intensity materials. So as we look forward to the next generation of maybe greener materials, you shouldn't forget that actually concrete is one of those materials, and it's one of the things we learn from the many things we learned from Ramon. There's a few other things some things I learned from Ramon, pieces of information that concrete is both a science and an art. I think Carlos talked about this too. It is a science. It is not a mystery. Okay, the concrete will tell you what it's doing. And, he used to, I remember both Ramon and Joe Ura both used to say this. If you stare at a structure, it'll tell you what it wants to do. It'll tell you how its loads are going to be distributed. It'll tell you how it wants to be treated over time. You will be able to see it even after a few years. You'll notice whether it needs assistance or you did it right. And it's not, you don't have to wait 50 years to figure that out. It'll happen soon. And so as you get that instinct, and we try to teach our own students that, as you get that instinct to understand that stiffness follows, loading, stresses and so forth, the same thing is true of these materials. That as we pay attention to them, they talk to us, and we understand how to combine the science and art of concrete. That we need to keep learning. We need to not confine ourselves with whatever we did our PhD in. That's the only thing we're going to do the rest of our lives. I can't think of very many successful PhDs who continue to do the same thing they did in their studies. They find other things to learn. They're lifelong learners. Look ahead and keep moving. Ramon never stopped moving, for God's sakes. I don't know how you live with him living. The fact is, he was 100 miles an hour all the time. He was on a plane somewhere. And if he's not on a plane, and even when he's on the plane, he's reading something. And, he's reading a report probably for Carlos or something. And, I was sitting one day in a courtroom with him for 3 days. We were trying to convince a federal judge about the meaning of cement. This is the only thing we were talking about for 3 straight days, 8 hours a day. What is the meaning of the word cement in a contract? Okay, we won the case, okay? But in those 3 days, we just sat in a courtroom and argued about the word cement. And whenever it wasn't his turn, he's sitting there with another binder of crap, reading, I don't, it's probably some other case, I don't know. But, he's constantly learning and paying attention to what the other side is arguing and so forth. But don't stop learning. And you keep this moving. Also, the fundamentals still work. Okay? So you pay attention to the fundamentals. They're not violated typically. Science works. Okay? This happens to be Pepe Esquerdo walking in a big 5th or 16th century crane. Okay? You have the idea that how do people lift up big blocks, or how do you move? How do you make structures years ago? Go back and study those things and understand that those fundamentals still work every single day. There are other impacts of this long-term life, and fly ash reduced the interruption in commercial enterprises. When you don't have to rebuild something, when you don't have to shut it down, when it always operates every day, when you go there in that silo, it's a fly ash silo, it's a wheat silo, it's a cement silo, it works every single day. That is gold for companies from a commercial standpoint. And so to make sure that you design and build things that don't have to go down because they need a lot of maintenance. And same thing, we look at the Bureau of Reclamation, those dams that we build, everything from the Hoover Dam to the Hungry Horse Dam. These dams operate for 70 years or 100 years, and we're still operating them. And we didn't have to tear them down. I should have said on the last one, and continuous operation when there's an emergency. When do you need a fire station? When there's an emergency. When you have a hurricane or a tornado or an earthquake, you need all of these kinds of things to function. And concrete, we can design structures like that. And that's something to remember of the lessons we get. We're now moving maybe more toward endurance-based design. We see this integrated structural systems. We look at advanced materials. But we also have to look at this toughness of structures and toughness of materials. And these are things that, again, this endurance of what we design every day. We don't make disposable stuff. And this is one of the fundamental things I think we see at ACI, and most of us are committed to this idea of quality concrete, of innovation in concrete. But, we're not designing something to fall apart next week. Okay, right now we're looking at, I know that we've got some colleagues looking at what is the concrete platform by which SpaceX launches off of? It basically destroys the slab, every single time. And you got to rebuild it or fix it. So why don't we build a slab somehow that can take this enormous heat? And that's being done right now. It's not going to be concrete. It's going to be out of a different material. It's a crazy material, but it'll be something else. But the foundations will be concrete, probably. When we look at passive energy, more recently, this is a floor that I designed. We're storing energy, geothermal energy, in a concrete floor. So we built a building that had to have a 4-foot thick floor. So we just heat it and cool it every year with geothermal energy, and it's basically like a giant ice cube in the summer, and it's a nice heating element in the winter. And in Oklahoma, that's all you need, right? And so you don't have to, you can only heat and cool this thing when energy is cheap. You never have to demand, whenever high demand is there, you never need it. Because this thing here, it takes 6 weeks for it to change the temperature by 5 degrees. So, why not use it to do the kinds of things? And now we see people putting shear walls in buildings that have the same elements. An interior shear wall that's heated and cooled with geothermal now creates steadying temperature inside of a building, and so it reduces your heating and cooling bills. But it's because of the concrete mass. So we're using the concrete not for structure or for durability, we're using it for mass. And the final lessons we learn is no matter how long it's been, reach out. I learned this from Ramon the hard way, I think. Ramon and I we'd gone our separate ways. I had been a professor for, 10 years. I was living in Pennsylvania, had Penn State at the time. And all of a sudden I get a call, it's like on a Wednesday. And it's Ramon on the phone. Ramon never called me back in those days. I was his long-lost student. He calls me and says, I heard you got married and you have kids. I said, I do, and I have kids, yeah. He says, well, why don't I take you and your wife out to dinner? I said, well, we live in Pennsylvania, State College, in the middle of nowhere in Pennsylvania, and there's no airport here. At the time, there was no airport in State College. And he goes, okay, how about Friday night? I said, fine, I'll see you Friday night. So Friday afternoon, about 4 o'clock, he shows up at my house in State College, Pennsylvania. Flew into Harrisburg and took us to dinner. My wife had never met Ramon, and I tried to give her a little warning that this is a different kind of person in life, okay? He's a hunter, and especially in the middle of Pennsylvania, okay? That he's more robust than most people you have ever met, and his humor won't be the same as you're used to. And he didn't let us down. He was 100% Ramon for dinner. And it was a blast, but the fact that he reached out and said, I really want to stay connected, and I really want to know you and your family and care for you. And then he stayed in touch with us for the rest of our lives. And my kids got to know him, and they loved him. Laugh and have a good story. So there's a lot of stories that can't be told in public anymore. He told those stories in public, okay? But the one that's clean enough to tell, okay, is the story of the emus, okay? So Ramon did all kinds of crazy stuff in life, but one year he decided that he was going to have emus. Okay, so he had a farm which he had a couple of bulls on, and so he bought a couple of emus because emu eggs sold for $500. And if you steal an emu's egg, it'll lay another one in about a week or so. So you just keep stealing the eggs, and you make $500 a week. And so that was a good deal. And so he had these emu eggs, and there were restaurants in New York City and other places that served omelets with emu eggs, I guess, or something. I don't know what the market was, but and then he could actually sell, if he hatched a few, he could sell emus. He could sell young emus for, $1,000 and all this kind of stuff. And then one year, about 8 months or a year after he bought the emus, the bottom dropped out of the fashion of emu omelets. Okay? And then, so I said, well, what are you going to do with your emus? He said, we already did it. Had the most expensive dinner of my lifetime. And then start the next chapter and don't wait. I think that's his untimely leaving us teaches us not to wait. To go on and do something cool in your life, and don't wait. Don't work yourself until you fall over. Go find a way to embrace life and start a new chapter and do something cool. And I think he was on the way to do that. Should have done it faster. He did everything fast, but that wasn't fast enough. All right. Well, thank you very much.